Hello. Through this video, I shall help you understand process capability measurements and how do you calculate them. The agenda of this video is to help you understand process capability measurements, do a recap of normal distribution curve, understand process capability ratios, understanding specification and the control limits, understanding Z-score, understanding DPMO, and Cpk. What is process capability? Process capability is the degree to which a system or service meets customer expectation, or it can also be mentioned as the ability of a process to produce defect-free products. There are three possible indices of process capability, namely Z-value, DPMO, and Cpk, PPPK. And while you intend to study process capability, it is recommended that you understand the normal distribution curve well. You may already know that for a known mean, if I were to add one standard deviation and subtract one standard deviation, the area under the curve shall be 68.26. If I were to add two standard deviation and subtract two standard deviation, it would roughly cover 95.44%, while plus minus 3 standard deviation will constitute 99.74% of the data. If you were to superimpose the customer specification, the upper specification limit, the lower specification limit, or either, you can get meaningful statistics about process performance. Anytime data goes beyond the specification limits, it shall be considered defect. Specification limits are mostly decided by the customer, who may give you one-sided or two-sided specification. In most service-related matrix, we would have one-sided specification. Let's say for an accuracy score, the customer has given you an accuracy score target of 95%, which means it is my LSL. Each time I do less than 95%, it shall be considered as a defect. On the other hand, sometimes, let's say for a handling time metric, the customer has given me a metric that the handling time should be 3 minutes, which is my upper specification limit. Each time a call or a transaction handling takes greater than 3 minutes, it shall be considered as defect. Sometimes in businesses, you may also have two-sided specification. It shall mostly be for dimensional data. Specification limits sometimes are self-imposed. As a part of your offering, you give yourself some specification for performance. Let's say a Domino's. It has given itself a target of supplying pizza in 30 minutes. And sometimes these specification limits come from the law of the land. The law of the land can also specify acceptance tolerance. And each time you cross the USL or the LSL, or whichever is applicable in your case, we are creating defects. So the entire gamut of study of process capability is about identifying how many times or what percentage do you cross the specification given to you by your customer. Area outside the specification limit is your failure area. The other term that you must understand here is control limit. Control limit, unlike the specification limit, are decided by the data itself. You collect data and your upper control limit and lower control limits are calculated from the data itself. Mostly, it shall be mean plus minus 3 standard deviation. Control limits are not provided by the customer. They represent the process performance. For a mature business process, the control limits should fit inside the specification limit. Because if the control limit were outside the specification, your process would surely create defects. Like in this case, if you see, my green line is inside the red line, which means my process is performing within this green line, while my customer expectation is the red line shown here. Let's now understand the Z-score. Z-score is one of the most common measures of process capability used in Six Sigma and outside. Z-score can be understood as number of standard deviations that fit between mean and the specification. Let's take an example. If I have a business process with a known mean and known lower specification limit and known upper specification limit, you are essentially saying how many standard deviations can I fit between mean and one of these specifications. That shall be the process capability or the Z-score of that side. Similarly, I'll do the same exercise for the other side. So USL and the mean. So between the distance between them, how many standard deviations can I fit between? That is what my Z-score is. Let's take an example. So if I have a mean, LSL and a USL, and I have a known standard deviation of 5, if the process is assumed to be normal with a mean of 10 and upper specification limit at 20, lower specification limit at 0, and a standard deviation of 5, Z-score is nothing but the count of standard deviation that I can fit between mean and the specification. Let me start from the Z on the upper side. So USL is 20, mean is 10. So the distance between 20 and 10 is 10. How many 5s can I fit between the 10? 2 times. So my Z on my upper side shall be 2. Similarly, on my lower side, the distance between mean and the lower specification limit is again 10. How many 5s do I fit between my 10? 2. So my Z on my upper side will be 2 and Z on my lower side will be 2. If I were to understand this using a formula, same mean at 10, lower specification limit at 0, upper specification at 20, and standard deviation at 5, Z USL uses the formula of USL minus mean upon standard deviation, while Z LSL uses the formula of mean minus the LSL upon standard deviation, which means 20 minus 10 upon 5, which is 2, and 10 minus 0 upon 5 on the lower side, again equal to 2. When you have two-sided specification, in real life, we may have two-sided or one-sided specification. Two-sided specifications are mostly applicable in dimensional data, like measurements. Let's understand a couple of examples. So let's say a cloth manufacturer has been asked by his customer for a cloth which should not be less than 140 centimeters and should not be greater than 160 centimeters. So he's given specification on both sides. Or while creating a door frame, a manufacturer is required to make door frames not greater than 5.01 feet and not less than 5.0 feet. Again, two-sided specification. You will very rarely find a service example. However, to quote one, my customer has mandated that the call handling time should not be greater than 3 minutes. However, he is also not okay with a call which is less than 30 seconds. So again, my upper specification limit being 3 minutes and my lower specification limit being 30 seconds. One-sided specifications are present almost everywhere. Let's understand a couple of manufacturing examples first. A biscuit manufacturer has been given a target that the breakage percentage should not exceed 1. So the management has instructed the production team to say that the breakage percentage should never exceed 1%. So my USL given to me by my customer, that's my management, is 1. Or a PPM target given to a firm at 1000. So the customer is saying that your parts per million defects should never exceed 1000. Or a leakage percentage acceptable to the customer in a compressor making process, again fixed at 1%. These are examples of one-sided specification. In the service side of life, if the customer has mandated that the call handling time should not be more than 3 minutes, my 3 minute is a upper specification limit. Exceeding that shall not be acceptable to my customer, hence it is a USL. At Advanced Innovation Group, the turnaround time for a Six Sigma Black Belt batch completion should not exceed 150 hours, upper specification limit. Or a motor insurance company saying that the claim closure TAT not to exceed 13 days. So again, 13 being my upper specification limit. You must understand that these specifications can be one-sided or two-sided. Most of the service-related metric will be one-sided specification only. You must understand whether your specification given to you by your customer is a USL or a LSL, because that will have a major bearing on your ability to calculate the Z scores correctly. Now let's understand how do we calculate Z for one-sided specification. Let's use a couple of examples. When you have only your upper specification limit available, assume you work with a claims management unit and you have SLA of handling time at 3 minutes. Anytime you take greater than 3 minutes, it shall be considered as defect. Should you look at calculating the Z score of the process? Follow the steps below. First, decide if this specification is USL or LSL in this case, because going beyond 3 is not acceptable to me. Hence, the 3-minute target given to me is my upper specification limit. Calculate from the data collected the mean and the standard deviation of the delivery TAT. Collect the data for the period you would want to study the process capability for. Once your data is collected, calculate the mean of the data and the standard deviation of the data. Let's assume that the mean came at 2 minutes and your standard deviation came at 1 minute. Use the formula now. Z on my upper side equals USL minus the mean upon standard deviation, which is my USL was 3 minus 2, which is my mean, divided by 1, which is 1. So if this were the statistics provided to me, I now know that the Z on my upper side equals 1. Because I don't have two-sided specification, so whatever Z I have received on my upper side shall be considered as the overall Z of the process. Similarly, if you have lower specification limit available only, let's take another example. As a part of the SLA that I've signed with my customer, the target of the accuracy score was given at 95%. Upon analysis of the audit scores, which I received from my quality team, we find that the mean is at 98% with a standard deviation of 1.5. Use the formula. Z LSL will be equal to mean minus the LSL upon standard deviation. Mean in this case is 98. So 98 minus 95, which is my target or LSL, upon standard deviation, which is 1.5. So 98 minus 95, which is 3. 3 divided by 1.5, which is 2. Because this is a one-sided metric, hence the Z LSL shall be considered as my final Z score of the process. So I will say that my Z is 2. When you set out to calculate Z for two-sided specification, let's say if we are under contractual obligation to deliver cloth between 140 centimeter and 120 centimeter, customer has mandated that cloth greater than 140 is not acceptable to him, less than 120 is not acceptable to him. As in a one-sided specification example, the first step shall be to calculate the mean and standard deviation of the produced cloth. Let us assume that the calculated mean is 130 and the standard deviation is 10. So the first thing you should do is to define the USL and the LSL of the process. In this case, my upper specification limit or USL shall be 140 and my lower specification limit shall be 120. Using the same formula of Z, USL and LSL, calculate the values. Z USL will be equal to USL minus the mean upon standard deviation, which is 140, minus mean, which is 130, upon 10, which is 1. While my Z LSL equals mean minus the LSL upon standard deviation. So my lower specification limit is 120. My mean is 130. So 130 minus 120 upon 10, which is again 1. So the capability on both sides is equal to 1. The next step shall be to look up the Z table to get the DPO values for the Z scores received for both sides. On the left side here, the numbers given to us in bold are the z-scores, and similarly on the top. These are your z-scores, while the values in front of them are your DPO scores. So if I were to look at the z value of 1, I get a DPO value of 1.59 E001. So my DPO of my upper specification limit is 1.59 E001. Remember that? It is mathematically equal to 1.59 by 10. My LSL is also the same. So my DPO LSL shall also be 1.59 E001. DPO USL that we've calculated at 1.59 by 10. DPO LSL we've looked at the Z table and found out to be 1.59 by 10. The next step for you would be to calculate the overall DPO. So add the DPO scores of the upper specification limit and the lower specification limit. To calculate the final DPO, we've added both of them up and we've received a value of 3.18 by 10 or 3.18 E001. Next step shall be to look up the Z table and find the Z score for the overall DPO received. Last time we looked at the Z table to find out the DPO scores. We wanted to find out the DPO score for a Z equal to 1. Now we got to do the reverse. Now we know the DPO scores and we want to find the Z value for that. We have to start searching for 3.18 E001. When you search, you see that the value closest to 3.18 is 3.19 E001, which is at 0.47. So my Z value, as I read from the Z table, is 0.47. Remember that the Z score found from the Z table is the Z long-term score. For short-term Z, add 1.5 to the Z long-term. So Z short-term equals Z long-term plus 1.5. Z short-term equals 0.47 plus 1.5, which is 1.97. So you can say that my long-term capability is 0.47, while my short-term capability is 1.97. The next measure of process capability is DPMO, or defect per million opportunities. You should remember that DPMO is nothing but DPO into a million. If you have known defect rate, you should look at calculating DPO. Once DPO is done, multiplying it with a million shall give you your DPMO score. Let me illustrate this using an example. While in the quality evaluation process, the QA involved audited 100 transactions, each with 20 checkpoints. Out of the several opportunities, the QA found 32 defects. You are now required to calculate the DPMO. You should first calculate the total opportunities available. Because there are 100 transactions and each transaction has 20 checkpoints, so total opportunities is 100 into 20, which is 2000. DPO is nothing but defects upon total opportunities. Number of defects that we have is 32. Total opportunities at 2000. So 32 by 2000 is my DPO score. Hence, my DPMO shall be equal to 32 by 2000 into a million, which you will calculate at 32,000. So here you will say that my DPMO score for the process is 32,000. Let's take another example. In a BPO operations, the quality team checked number of claims and marked the total number of issues they identified. Each claim has 7 opportunities of pass or fail, and you are required to now calculate the DPMO. I have here the number of claims that have been checked, and I have here the total number of issues that have been observed. One good start point for the DPMO calculation shall be to calculate the DPO scores. if you have to calculate DPO in this case, the first thing would be to find number of opportunities and then find the count of defects. In this example, issues that we've identified is 196 and total opportunities, when you add that claims checked column, is 4,223 because each claim has 7 opportunities. So 4223 into 7 is the total number of opportunities, which is at 29561. So my DPO will be 196 upon 29,561. So for my DPMO, DPO into a million, which means 196 by 29561 times a million, which is 6630358. So whenever you are calculating DPMO, first calculate the number of opportunities. Look at calculation of your DPO scores. When you have your DPO scores, multiply it with a million and you will get your DPMO scores. The next measure of process capability is Cpk. Cp is a measure of process potential index, also referred to as the inherent process capability, and is a measure of the capability of the process by design. Cp mathematically is calculated as customer tolerance upon normal distribution. So if I have a known USL LSL, Cp is nothing but the ratio of the customer specification, which is USL minus the LSL, and the normal distribution curve, which is nothing but 6 times the standard deviation. So my Cp essentially will use a formula USL minus the LSL upon 6 times the standard deviation. There are 3 possibilities. Cp can assume a value of 1. When Cp equals to 1, it essentially means that the USL LSL and the normal distribution have to be absolutely the same. In such a condition, you are essentially saying that the normal process is capable of creating products which meet customer specification 99.74% times. However, if any special variation happens in the process, we are almost sure to make defects. When Cp is less than 1, it can happen only when, for a known USL and LSL, my normal distribution curve is bigger than the customer specification, which would mean that even a normal process is incapable of producing products that meet customer specification. Cp greater than 1 would mean that the customer specification is greater than the normal distribution, which is that my normal process is capable of creating products that meet customer specification. However, even for special cause variation, there is a little cushion on both the sides. If the Cp value is less than 1, you are saying that by design itself, the process is incapable. If you see 1, it is acceptable, not fantastic. You're saying that 99.74% time, I'm good. Cp greater than 1 is what one should desire. The other measure is Cpk. You would want that your process center should always be at the specification center. For a known USL and LSL, I would want that my process mean should be exactly at the center of the specification. Let me quote numbers. So if my customer specification is 140 on the upper side and 120 on my lower side, I would want that my mean is exactly at 130. Exactly. Which means it should be equidistant from both these specifications. However, in reality, your process will shift. While you desired your process mean to be exactly at the specification center, it may move towards one of the specification. Like in this case, it has moved towards the upper specification limit. Cpk is a measure of process performance index. Remember Cp. Cp was inherent capability, what you're capable of. Cpk is a measure of the process performance. So it is referred to as the process performance index. We must measure the designed capability, that is a CP, and what we've actually performed as CPK. Mathematically, CPK is minimum of CP on my upper side and CP on my lower side. With CPU using a formula of USL minus mean upon 3 standard deviation and CPL using a formula of mean minus LSL upon 3 standard deviation. While you wanted your mean at the specification center, exactly between the specification, the actual mean may shift either side from the specification center. Whichever side the mean would have moved, you're more likely on that side to cross the customer specification. CPK is a measure of the same effect. For a known LSL and USL, if I know the mean of the process, I can easily understand if the mean has shifted towards the right or towards the left. In this case, USL is more likely to cross the USL and not the LSL. It has gone farther away from the LSL while it has gotten closer to the USL value. Hence, when you calculate the CPU and CPL, CPU shall be smaller and hence it shall become the CPK. Let's understand this through an example. So if I have known specification limits, so my upper specification at 100, lower at 20, I wanted my mean to be exactly at 60. While it moved and it has now gotten to 80. So my CP will be equal to USL minus LSL, which is 100 minus 20 upon 6 times the standard deviation. So if I'm assuming my standard deviation to be 10, then it is 80 upon 60, which is 1.33. Remember what I told you in the start? Compare the received CP to a benchmark of 1. Here, my CP value is greater than 1, so my business process is capable by design. Now let's look at what has happened to its performance. To calculate my CPK, I shall need to calculate my CPU and CPL. CPU will be equal to upper specification limit minus the mean upon 3 standard deviation, which is 100 minus 80 upon 30, which is 2 by 3 or 0.66. While my CPL will be equal to mean minus the LSL or 80 minus 20 upon 3 times 10. So 60 divided by 30, which is 2. We discussed that CPK shall be the smaller value between the CPU and CPL. Hence my CPK here will be 0.66. So while your capability was 1.33, you are actually doing 0.66. So CP value, which was 1.33, should be compared against the CPK value of 0.66. If you work at drawing inference from the values above, CP is greater than 1, which is at 1.33, which means that by design, the process is capable. CPK should always be compared against the CP. We are currently doing less than what we were capable of by design. And CP less than 1 is very bad for business. So only 66% time will we produce products that are capable of meeting the customer requirement. Simple takeaways. CP is the capability of the process by design, while CPK is the process performance index. Organizations shall have to make arrangements that CPK is equal to CP. You must understand that CP, CPK, CPU and CPL shall be equal when the desired mean and the actual mean of the process is the same. CPK less than 1 would mean that the process is not performing as per the customer specification. CPK can assume negative values when the mean exceeds the USL or the mean is less than the LSL. If mean exceeds the specification, CPK shall assume negative values. Look at the formula. CPU equals USL minus mean upon 3 standard deviation. So if my mean is greater than the USL, while my customer wanted me to not exceed 140 centimeters, and if mean itself has exceeded 140, my CPK shall become negative. Or if my customer wanted me to be not less than 120, going below 120, let's say my mean went to 110, my CPL will be equal to mean minus the LSL upon 3 standard deviation, which means if my mean is lesser than my lower specification limit, CPK shall become negative. I hope this gives you clarity about CPK. Now let's understand the relationship between Z-score, DPO score, DPMO score, fail percentage and pass percentage. For a known Z-score, you could look up the Z table and check for the DPO score. Multiply the DPO with 1,000,000 to get DPMO. To get fail percentage, multiply the DPO score with 100, and to get pass percentage, subtract the fail percentage from 100. So let's take an example. So if I am looking at a Z score of 1, when I look up the Z table, it shall give me a DPO value of 1.59 E001 or 1.59 by 10. If I were to multiply this with 1,000,000, it will become my DPMO. So 1,59,000 shall be my DPMO score at a Z score of 1. If I wanted it in terms of the fail percentage, 1.59 by 10 times 100 or 15.9 shall be my fail percentage if my Z score is 1. If I want to mention it positively, I can say 100 minus 15.9 or 84.1 will be my pass percentage. It is important for you to draw this grid for yourself. So when you have a Z score, adding 1.5 will give you your short-term score. Looking up the Z table will give you the DPO score. Multiplying DPO with 1,000,000 will give you DPMO. DPO times 100 will give you fail percentage. 100 minus the fail percentage shall give you your pass percentage. Let's look at the value of Z score at 2. So when I have a Z score given to me at 2, if I add 1.5, which is 3.5, that's my short-term process capability, short-term Z score. So ZST will be 2 plus 1.5, which is 3.5. Look up the Z table for the value of 2. You will get a value of 2.28 E002, which is 2.28 by 100. If I were to multiply this with 1,000,000, I'll get the DPMO score. So 2.28 by 100 into 1,000,000 will give me 22,800, which is my DPMO score. To calculate my fail percentage, 2.28 by 100 into 100, which is 2.28. So if my process is performing at Z score of 2, my fail percentage of the process will be 2.28. To understand pass, I'll do 100 minus 2.28 or 97.72% will be my pass score if my Z of the process is at 2. I hope this video helps you understand process capability. Look forward to further videos on how to calculate this using Excels and Minute apps, which we've also recorded. Thank you.